So let's analyze this carbon. We can see, based on the periodic table, that carbon is supposed to have 4 electrons. And we know that based on the location of carbon in the periodic table. So we know carbon is supposed to have 4 valence electrons. However, if we count the number of valence electrons on this carbon, we would count 1, 2, 3, 4, 5. So this carbon has 5 valence electrons. And we know if we take the number of valence electrons an atom is supposed to have and subtract it by the number of valence electrons the atom actually has, that will give us the formal charge, which would give us -1. So we know this carbon has a formal charge of -1, which means it has this localized negative charge, the charge of 1 electron. That's why it's -1. What about this carbon? Well, again, we know carbon, based on where it is in the periodic table, is supposed to have 4 valence electrons. However, this particular carbon has 1, 2, 3 valence electrons. So we know we take the number of valence electrons an atom's supposed to have and subtract it by the amount it actually has, and that gives you the formal charge, which would give us +1. So we see this carbon has a formal charge of +1, the charge of essentially 1 proton. But the point is this carbon has localized negative charge, while this carbon has localized positive charge. And we can tell that based on the formal charge. So that's going to make these two carbons want to react, because we know opposites attract. So now in a thought experiment, imagine we have these 2 electrons, and we know these electrons are going to have this localized negative charge density. So we know these electrons are going to want to repel each other. And if we were to squish these electrons together, what's going to happen? If we squish these electrons together, we're going to have this region of high negative charge density, this high charge density region, which is very energetically unfavorable, and this is not stable. And in fact, we know with Coulomb's law, the closer the 2 charges are, the higher the electric potential energy in the system. And again, that's physics, don't worry about it too much, but the point is, if we squish these 2 negatively charged electrons nearby each other, we're going to have this region of very high negative charge density, which is very energetically unfavorable, and this is unstable. And these 2 electrons are going to want to repel each other. They're going to want to repel each other to minimize that charge density. So the rule of thumb is nature hates localized charge, and nature always wants to minimize localized charge. Nature doesn't like having high localized charge because that's high in energy and that's very unstable. So nature always wants to minimize localized charge density. So another example is, imagine we have this electron and this proton. So we know this electron has localized negative charge density and this proton has localized positive charge density. So we know these guys are going to attract each other. Why? Well, when they react, they're going to cancel out charge density. They're going to cancel each other out, so we're going to have this region of no charge density. So we've effectively minimized charge density because we canceled out charge density. So this is energetically favorable. And that's why negatively charged electrons and negatively charged protons want to react. So that's essentially what's going to happen with these 2 carbons. We know this carbon has a formal charge of -1. So therefore it has localized negative charge. While this carbon has a formal charge of +1. So it has localized positive charge. So that's unstable. This is localized negative charge, and this is localized positive charge. That's unstable. However, if these 2 carbons react with each other, they essentially form a bond and they destroy that localized charge, because now if you were to see the formal charge of this carbon, it would be 0. And the formal charge of this carbon would be 0. So we've essentially destroyed that localized charge, and now we have this neutral molecule. So we've minimized charge density. So this is energetically favorable. And in fact, that's the basis for nearly every chemical reaction you'll see in organic chemistry. It's essentially localized negative charge wanting to react with localized positive charge, so these charges can destroy each other. So just a bit of terminology, The compound that has localized negative charge is referred to as a nucleophile, and the compound with localized positive charge is referred to as an electrophile. So whenever you see a chemical reaction in organic chemistry, there's going to be a nucleophile with localized negative charge and an electrophile with localized positive charge. So let's do another example. We have this carbon with a formal charge of -1. And you could use that formula I spoke about earlier, and you would see this carbon has a formal charge of -1. So therefore it has localized negative charge density. That's unstable. What about this carbon? Well, if you were to find the formal charge of this carbon, it would be 0. This carbon has a formal charge of 0. However, something important to realize is this chlorine is a lot more electronegative than carbon. And we know that based on the periodic table trends, where as you go to the right in the periodic table, the elements get more electronegative. So we see chlorine, which is all the way over here to the right, means that chlorine is a very electronegative. And in fact, these are the values. Chlorine has an electronegativity of 3.16, while carbon has an electronegativity of 2.55. So therefore, carbon is very electronegative. So what does that mean? That means chlorine really likes negative charge. It really pulls on negative charge density. And the reason is a little complicating. It's due to the Zef nuclear charge, which means in its nucleus it has positive charge. But the point is this chlorine is much more electronegative than this carbon. So therefore, all these electrons on this carbon are going to be attracted to this chlorine. So as that negative charge density is attracted to the chlorine, what's going to happen is this chlorine is going to hog the negative charge density, so it's going to have a partial negative charge. And this carbon is going to have a partial positive charge. Because again, all that negative charge density is being hogged by the chlorine. So this carbon is losing a negative charge density, so now it has a partial positive charge. So whenever you see the symbol, that refers to a partial charge. But again, the point is carbon and chlorine, they have different electronegativities, where chlorine has a higher electronegativity, so it's going to pull negative charge density, so it's going to have a partial negative charge, while this carbon has a partial positive charge. So again, this is localized charge. This is localized positive charge, and this is localized negative charge. So what's going to happen? Well, we know this carbon has a partial positive charge, so localized positive charge, while this carbon has a formal charge of -1, so it has localized negative charge. So therefore, these carbons are going to want to react. And what happens is these lone pairs of electrons essentially attack this carbon, which allows these electrons to fall on this chlorine, essentially forming this product. So now we form these products. And in fact, this is a lot more stable. Why? Well, if you were to do some accounting, in this original condition, you would see we have one formal charge and we have two partial charges. However, in these final conditions, we have one formal charge and no partial charges. So we can see in these original conditions, we have a lot more localized charge, and in these final conditions, we have less localized charge. And not just that, if we were to have a formal negative charge on carbon versus chlorine, we would want that negative charge on chlorine. Why? Well, again, chlorine is more electronegative, so it likes negative charge. And not just that, chlorine is a lot larger. It has a larger ionic radii, so therefore this formal charge of -1 is delocalized around a larger atom. So therefore that formal charge of -1 is spread out over a larger atom, so it's less charge density. That charge is spread out through a larger volume, so less charge density. So now we can see why these after conditions are more favorable. So again, all chemical reactions you see in organic chemistry will have a nucleophile with localized negative charge and an electrophile with localized positive charge, and when they react, they destroy charges, and we have less charge density. So here are some common nucleophiles you'll see in biochemistry, and here are some common electrophiles. So what are some common themes we see? Well, we see a lot of these nucleophiles have these lone pairs of electrons. Because again, when we have a lone pair of electrons, we have an orbital with these two electrons. So we have some localized negative charge. We have a partial negative charge here. So again, whenever we have a lone pair of electrons, we have some partial negative charge. And not just that, Again, we know the sulfur is more electronegative than carbon, so it's also pulling some negative charge density. So again, that's why we have this partial charge. We know this carbon, if we were to find the formal charge, we would have a formal charge of -1. So again, here we would have a partial charge. Here we would have partial charge, negative charges. Here we have a formal charge of -1, which is actually stronger negative charge density. So therefore, this is a stronger nucleophile. The more negative charge you have, the stronger the nucleophile. So formal charges of -1 is more negative charge than a partial charge. But again, we have these lone pairs of electrons, so we have these partial charges. So again, but whenever we have some localized negative charge, we have nucleophiles. So what are some common themes of these electrophiles? Well, common theme is, you'll see, for example, let's look at this molecule. We have this carbon with an electronegativity of 2.55, and we have this oxygen with an electronegativity of 3.44. So we know this oxygen is more electronegative than this carbon. So if this oxygen is more electronegative, we know it's greedy. It's going to hog that negative charge density. It's going to steal some of that negative charge density. So when it steals some of that negative charge density, now it steals some negative charge, so this carbon loses some negative charge. So when this carbon loses some negative charge, it gets a partial positive charge. So that's a common theme with electrophiles. You'll see one atom next to another atom that's more electronegative. So the atom that's more electronegative is stealing negative charge, creating a partial positive charge. So that's where we see our electrophiles. That's a common theme you'll see with electrophiles. So again, here's another electrophile, because again, we have a carbon next to nitrogen. Nitrogen is more electronegative, so it steals negative charge. It hogs some negative charge density, so we have a partial positive charge. Here, we have this phosphate next to these oxygens. We know oxygen is very electronegative. So we have all these oxygens stealing negative charge density. So this phosphate is going to lose a lot of negative charge density. All these oxygens are stealing negative charge density. So this phosphate is very electron deficient. So we have this strong partial positive charge. So this phosphate is electrophilic. So again, that's a common theme with electrophiles. But again, we know there's a difference between a partial charge and a formal charge. We know, for example, this carbon and this fluorine, we know this fluorine is more electronegative. So this fluorine is stealing negative charge density. So we have this partial positive charge. But here we have a formal charge of +1. Because again, we would find the number of valence electrons carbon's supposed to have. Then we would find the number of valence electrons carbon actually has to find the formal charge. So again, formal charges are stronger than partial charges. So this would be the strongest electrophile. This guy with this formal charges is the strongest electrophile. And then these would be weaker electrophiles. But again, so that's the common theme with electrophiles, either partial, formal, positive charges or these partial charges. But now, so we know we have these nucleophiles and these electrophiles, and we can have these nucleophiles react with these electrophiles, and we can mix and match these reactions. For example, maybe this nucleophile reacts with this electrophile, or maybe this nucleophile reacts with this electrophile, or maybe this nucleophile reacts with this electrophile, etc. Whenever we have localized negative charge and localized positive charge, we can have a reaction. So let's do an example. Let's say we have this nucleophile and this electrophile. We know they can react. We have this localized negative charge with this lone pair of electrons, and we have this localized positive charge, because again, this oxygen is hogging negative charge density. So again, we have that partial positive and partial negative. So again, nature hates charges. It wants to destroy these charges. So now these molecules will react. So these electrons will attack, forming a bond. And when we form that bond, we push these pi electrons up on this oxygen. So when we do that, we form this high energy intermediate, and then the electrons will move, forming this product. So now we've reacted the molecules together. And again, the idea was this molecule had some negative charge, this molecule had some positive charge, so they attracted and they reacted to form this molecule. So again, the molecule with the negative charge is the nucleophile, while the molecule with the positive charge is the electrophile. So we have this nucleophile react with this electrophile. But something really important to realize is, let's say we had this nucleophile and an electrophile, and let's say we were in an acidic solution. So let's say we were in an acidic solution with a lot of hydrogen ions, and really we would have a lot of hydronium. But what happens when we're in an acidic solution? We're going to protonate these molecules. So we're going to protonate this oxygen. So what happens when we protonate this oxygen? Well, now it gets protonated, and when it gets protonated, now it has a formal charge of +1. So now we have strong positive charge density. So what's going to happen when we have strong positive charge density on this oxygen? It's going to pull negative charges even stronger. When we have this formal charge of positive 1, it's going to really strongly pull on negative charges. So it's going to steal very strongly, it's going to steal negative charge density. All these electrons here, this positive charge is going to pull on those negative charged electrons. So we're going to strongly pull electron density, negative charge density. So we're going to create a stronger electrophile. We're going to create a stronger electrophile, and we're going to create a more reactive electrophile. So again, originally we had an electrophile. However, we protonate this guy. Now it pulls more negative charge, creating a stronger electrophile. So now we have a more reactive electrophile. So the rule of thumb is that acidic conditions create stronger electrophiles. So that's a general rule of thumb. For example, let's say we had this electrophile. What would happen if we put it in an acidic solution and it got protonated? Well, if it gets protonated, now we have this formal charge of positive 1, which pulls more negative charge density, creating a stronger electrophile. So again, the point is acidic solutions create stronger electrophiles, stronger partial positive charges, and more reactive electrophiles. And sometimes you hear about reaction being acid-catalyzed. A lot of the time, that's why. Because certain reactions can be acid-catalyzed, because when we protonate it in acidic solutions, we create more stronger electrophiles. So again, acidic solutions create stronger electrophiles. However, let's say we have the same reaction, and let's say we have this reaction in a basic solution with high hydroxide. So in a basic solution, what's going to happen? Well, that hydroxide, that basic solution, is going to deprotonate the nucleophile. And when it deprotonates the nucleophile, we create this formal charge of negative 1, so we create a stronger nucleophile. So again, originally, we had this partial negative charge, but we're in a basic solution, so we steal hydrogens, create a formal negative charge, so now we have a stronger nucleophile. So the rule of thumb is that basic conditions create stronger nucleophiles. Basic conditions create stronger nucleophiles. For example, let's say we had this nucleophile. We have this nucleophile with this partial negative charge. However, if we put it in a basic solution, it's going to deprotonate that hydrogen, forming this formal negative charge of negative 1, creating a stronger nucleophile, because now we have a formal charge of negative 1. So now we have a stronger nucleophile, a more reactive nucleophile. So basic conditions make stronger nucleophiles. So normally we have a hierarchy. For example, we know this carbon is electrophilic because look, it has 1, 2, 3 bonds to oxygen. And we know oxygen is very electronegative, hogging electron density, stealing negative charge density. So therefore, we're going to have a relatively electrophilic carbon. How about this carbon? Well, it has 2 bonds to oxygen. So again, oxygen's electronegative, it's hogging negative charge density, so we're going to have an electrophile. How about this carbon? It has 1 bond to oxygen, which is going to pull negative charge density. So we're going to have this hierarchy. This carbon's going to be most electrophilic with the highest partial positive charge, so it's going to be most electrophilic because it has 3 bonds to oxygen. And then this guy will be less electrophilic because it only has 2 bonds, and this guy will be even less electrophilic because it has 1 bond. And this carbon is not going to be electrophilic because again, hydrogen and carbons have the same electronegativity, so there's no partial positive charge here. So this atom is not very electrophilic. Then again, but remember, formal charges are the most reactive. So this carbon with the formal charge of positive 1 would be the most electrophilic. So we would have this hierarchy. This is the most electrophilic, this is the least electrophilic. And what if we had this atom? Well, again, this carbon has 2 bonds to oxygen and 1 bond to nitrogen. And we know nitrogen is more electrophilic, more electronegative than carbon, so it's still pulling some negative charge density. So this carbon electrophilic reactivity would be around here, because here we have 3 bonds to oxygen, here we have 2 bonds to oxygen and 1 bond to nitrogen, and here we have 2 bonds to oxygen. So this would be the most electrophilic, then this guy, then this guy, then this guy, etc. And what about nucleophiles? Well, again, this oxygen has a formal charge of negative 1, while this oxygen has a partial negative charge. So this is more stronger negative charge density, so this is a stronger electrophile. Then this guy's a little weaker. And what about comparing this oxygen to this fluorine? Well, this fluorine is very electronegative. So something important to realize is because this fluorine is electronegative, it wants to hog all its negative charge. It wants to keep these lone pairs of electrons and hog all that negative charge. So therefore, we know for this to act as a nucleophile, these electrons have to attack and it has to donate these electrons. But this fluorine being so electronegative, it wants to hog the negative charges. It wants to hog these lone pairs of electrons, so it doesn't want to donate them, so it's not very nucleophilic. And then this carbon has no lone pairs of electrons, so it's not nucleophilic at all. It's a very weak nucleophile. And this iodine, we see it has this formal charge of -1, so it has a lot of localized negative charge, so it's a strong nucleophile. And not just that, this is a large atom. It's a large atom with these large orbitals, so it's more polarizable, so these negative charge density can more easily attack, which makes it more nucleophilic. But again, so we have this hierarchy. But the key point is, formal charges are more nucleophilic than partial charges. And when comparing the atoms, the more electronegative, the weaker the nucleophile. So again, we have this hierarchy, but notice something. These carbon molecules are not very reactive. This is a very weak electrophile, and this is a very weak nucleophile. So we know these carbon skeletons are not very reactive. And in fact, that's precisely why a lot of life is built upon these carbon molecules. For example, we have these fatty acids, which have these carbon skeletons, and these carbohydrates, which have these carbon-carbon bonds, and these proteins and polypeptides, which have a lot of carbon-carbon interactions. Because these carbons are very stable. They're very stable. They're not very reactive. This isn't very electrophilic, and this isn't very nucleophilic. So they're very stable, and they're not very reactive. So they make good components of life for organic molecules and for life because they're not very reactive. So now let's say we had this nucleophile with this formal charge of -1, so we have this nucleophile. We know it's going to want to react with these molecules. So which molecules are going to react with? When this nucleophile is looking at these molecules, what is it going to see? Well, it's going to see the charges. For example, we have this formal charge of -1, we have a formal charge of -1. So again, but here we have a partial positive charge. So that's a good candidate because we have this negative charge nucleophile. So we have this partial positive charge, so that's a good candidate for a reaction. And here we also have a partial positive charge. But notice here we have a carbon bonded to 3 oxygens. Here we have a carbon bonded to 2 oxygens. So this carbon is going to be more electrophilic. More oxygens are stealing negative charge, so we're going to have a stronger partial positive charge on this carbon. So this is a strong electrophile, so this is a good candidate for a reaction. We also have some other relatively electrophilic carbons, and then here we have very tiny electrophilic carbons, because again, they're bonded to oxygen, pulling negative charge density. But again, this nitrogen wants to react, and it's going to look, what is the best molecule to react with? And we see this is the most positive molecule, and this is the most negative molecule, so therefore these molecules are going to react. All this nitrogen sees are these positive charges, because it's looking for a positive charge to react with. So this is the reaction we're going to have. However, something important to realize is this localized negative charge creates a nucleophile, and this localized positive charge creates an electrophile. However, this nucleophilicity is a kinetic property. If this molecule is a strong nucleophile, that's a kinetic property. And that just means it's a strong nucleophile. It has a lot of negative charge, so it's going to react quickly. It's a kinetic property. Nucleophilicity and electrophilicity are kinetic properties. It says the rate that this reaction is going to react, how quickly these reactions are going to react. If this is a strong nucleophile, it's going to react quickly. If this is a strong electrophile, it's going to react quickly. It's going to have high kinetics. However, when this reacts, it's going to form a bond, and then this bond's going to break, and these electrons are going to fall on this guy. We're going to form these products. However, these products are incredibly unstable. We have this formal negative charge of 2, -2 charge, which is incredibly unstable. So then it's going to react, reforming these original molecules. So therefore, just because this is a strong nucleophile and this is a strong electrophile, that means, yeah, they're going to react quickly, but it doesn't mean this reaction is going to be very stable. And once this reaction reaches equilibrium, once this reaction reaches equilibrium, the vast majority of the molecules are going to be in the form of these original molecules. So just because this is a strong nucleophile and strong electrophile doesn't mean when it reacts, it's going to favor these products. And in order to determine once once this reaction reaches equilibrium, if it's going to favor these guys or these guys. In order to determine that, we need to quantify the stability of this guy and compare it to the stability of this guy. So how do we do that? Well, what we need to do is we need to imagine this guy as an acid and find the pKa. If we find the pKa of this guy acting as an acid, the pKa of this guy will tell us about the stability of this conjugate base. And then finding the pKa of this guy will tell us the stability of this conjugate base. So finding out the pKa's of these acids, we can quantitatively determine the stability of these guys. So therefore we can determine the stability of these guys and determine once this reaction reaches equilibrium, will it favor these molecules or these molecules. So if you're interested in these pKa's and how to